Hi guys, can we do a sound check?
All good.
Okay, great, thanks. How was the midterm?
It was something.
What's that?
It was something.
Was something? Hopefully it wasn't too bad. Okay, guys, let's get started here. Let's see. Where were we? I think where we um, where we were, I guess, is going back a week and a half now. So before the um, before the break. So we were coming up with first we talked about ways to calculate the transfer function of an inverter. I think this was in the test. Okay, and then we started looking at how can we do simplifying models for the inverter or a gate so that we could do some quick hand analysis of it. So the idea ended up being that we have, let's see, where should I go with this? So that, okay, good. I'll do it here. So that we can, basically there's, for each process, we can do a estimated value, like we could for each. Okay, I'm sorry, trying to think of what's the best way to say it. So if we could do a really simplified model of a transistor in a CMOS gate, okay, and that model would have a capacitance on the drain. It would have an equivalent resistance. It would have an effective switch. It would have a capacitance on the source, and it would have a capacitance on the gate. Okay, and so for each process, we could come up with a value of R sub n, which is resistance of, what should I call it? Let's call it equivalent. Or equivalent isn't really a good word. Can't come up with a good word here, but let's call it equivalent for now. Equivalent resistance of NMOS for simple delay calculation. Now, this is going back to realizing that, say, for example, when the input of our inverter goes from low to high, our output, so this is the input goes from 0 to VDD. Our output for this would go from VDD to ground. Oops, let me just draw it. Okay, so if we looked at what would happen to, so, assuming this is, and we assume this is like very fast. So we don't really see a rise time here. It's, let's say it's a picosecond or something, like very, very quickly. So immediately the PMOS would turn off, the NMOS would turn on, and then drain the output node to ground. Okay, so that's what's happening here. The input of the NMOS went from being off to being on, and then it started draining this thing, and then that's why the output went down. Now what's happening is, so if you look at the IV curves of an NMOSFET, so VDS, IDS, and so we went from sort of like, so this would be for VGS is equal to 0 to, VGS is equal to VDD, okay? Almost immediately we went up to here, okay, because the VGS jumped to VDD, okay? And then the VDS starts draining off. So VDS, the current coming out of the NMOS is going to do like this. It's going to change as VDS gets less and less. The current from the NMOS at any point is going to go down. Okay, so what this R sub n value is we're saying if you wanted to pretend like the NMOS was just a resistor, like we're doing here, okay, it would be as if it had at each one of those points, it would be as if it had a particular resistance like this, right? Because this is, so resistance is equal to V over I. So sort of the inverse of this curve at any point is the, sorry, no, I don't want to say that, because the resistance would have to go through, the way we've drawn the resistor, it's going, once this switch is on, the resistor is going to go through, so this guy would be connected to ground in that case. So it would be this resistance or this resistance, and these would be the 1 over R values that this equivalent resistor, would move between. So R sub n is the average of those values. Okay, so that we basically come up with an R sub n value for a particular process, and we plug that in, and it turns into a pretty simplified model. And we saw that, where was it? That if we use this really sort of simplified model with this effective resistance and the capacitance also, we have effective capacitances, in aggregate, we get a pretty good model. If you just look at the delay, the 50% delay through the device, or the 10 to 90% curve, we end up, so this would be this dashed line is the RC model. It's just just this really simple R effective. And then the splice model, and they're pretty close. At each one of these points, there's a difference, certainly going to here. There's a difference between them. But if you just looked at the delay, there's not a big difference between these 2 points. So if I just looked at the prop delay using this R effective, it's not actually going to give me a very big error. And if I looked at the rise and fall time delay, it's also not going to give me a huge error. It might give me like a 10-15% error, but enough for a hand calculation. And then I only have to worry about having a RC model. Okay, so if you look in the book in chapter 8, you'll see that our process, which is the 0.18 micron TSMC process, the N MOSFETs have a particular value for R sub n. Okay, and that's given in terms of resistance per unit width. So I forgot what it is. I think it's around 2 point something kilo ohms per micron. Okay, and so you can use that, right? And then if you have a 1 micron wide device, you use a resistance of 2.7 kilo ohms. If you have a 10 micron wide NMOS device, use a resistance of 270 ohms. So resistance, the wider you make this device, the resistance goes down by the width, just directly ratioed. And the capacitances, these C sub Ds, etc., are also given in terms of, and again, I don't remember, let's say it's around 2 femtofarads per micron. They're also given assuming that the length of the device is a minimum length device. And so as you make the device wider and wider, the resistance goes down, the capacitances all go up. The gate capacitance, drain capacitance, source capacitance. Okay, and you can do the same thing for a PMOS device in a particular process. And that looks like, that also looks like a switch, a resistance, capacitance at the drain. And this capacitance really goes to VDD, but because for the purposes of RC time constants, whether it's hooked up to VDD, to ground, or to some other constant supply, it doesn't matter. So we can just pretend like those all end up in parallel, as we'll see. And so the source is also hooked up to VDD. Okay, and the gate is also to VDD. Okay, so similar model for the PMOS. And so we also saw, so R sub P will be also some equivalent resistance. I want to say aggregate resistance, maybe is a better word. I don't know, because it's on sort of this average. So you're sort of aggregating the resistance while this thing is transitioning. So equivalent resistance, I guess. And then we said that typically R sub P is 2 to 3 times R sub n, because the current gain of a PMOS transistor is usually 2 to 3 times less than the current gain of an NMOS transistor. Okay, so that makes the resistance of the PMOS higher in this simplified model. But the capacitances are about the same. So C sub D for a PMOS or C sub S for a PMOS. C sub D for a P is about equal to C sub S for a P is about equal to the drain and source capacitances for the NMOS. So they're all kind of similar. If you look at the table in chapter 8, it'll be like, they're all around 2 femtofarads or something per micron. Okay, and then the gates, so C sub G of N is exactly the same as C sub G of P, because the gate capacitances get made at the same time. Okay, so we end up with this really simplified model. This kind of talks about all this stuff. And, with it, we can do this really, it didn't seem so simple, but believe me, it's a lot simpler than doing a hand calculations with these weird IV curves and all that kind of stuff. And we ended up with this delay of 6RC for an inverter. Okay, so if you have an inverter driving another inverter, the delay ends up being 6RC. Okay, and that's whether you have a, so I'm sorry, let me take it back. So if you have a minimum size inverter driving another minimum size inverter, the delay in the simplified assumption is 6RC. Okay, so regardless of whether you're in a 65 nanometer process or a 180 nanometer process, it's 6RC is the delay for a minimum size inverter driving another minimum size inverter. Now, what's the difference between the 65 nanometer and the 180 nanometer process is the R sub N, R sub P, Cs. These are different for this process compared to this process. So for example, I think it's given here, if you look at the RC for a 65 nanometer process here, seems like it's 1.25 kilo ohms microns times 1 femtofarad. So this is RC for 65 nanometer process. Let me calculate that. Okay, so this gives me 1.25 femto, sorry, yeah, 2.25 picoseconds, sorry, picoseconds. And let's say if you remember the RC numbers, if I remember them correctly for our 180 nanometer process, it was 2.75 kilo ohm micron times 2 femtofarads. So that ends up being 5.5 picoseconds. Okay, so using the same 6RC thing, so for a 65 nanometer process, this delay for that one resistor, for one inverter, is 6 times 1.25 picoseconds. So if it's delay of 65 nanometer, so 1.25, oops. So that ends up being 7.5 picoseconds. And then for the 180 nanometer process is 6 times 5 point, what do you say, 5.5 picoseconds. So this is more like 33 picoseconds. Okay, so a much longer delay for the bigger process, which is what we would expect. So you can see like there's several sort of degrees of simplification here, which is nice because we know that regardless, if we have a minimum size inverter driving another minimum size inverter, whether it's in whatever process we're in, it's going to have this 6 RC delay, and I can just multiply that by the RC of a particular process to figure out the actual delay in that process. So when would you want to do that? Well, so when you're designing a chip, a lot of times, especially at the beginning, you use these things a lot at the beginning of a design project. So, and a lot of times when you're designing a chip, the first question to ask is, what process do I need to be in? Remembering back to our first or second lecture, you guys remember that a 65 nanometer process is significantly more expensive than a 180 nanometer process. So it comes down to pricing. So what you would do is you'd come up with, you know, like if you're looking at whether a particular process has the speed, you want to pick the biggest process that can meet your speed requirement from a design cost standpoint. So what you would do is you would come up with the fastest sort of circuit path that you would need. You would get these values, you'd get it in terms of these RC constants, you know, do a bunch of RC calculations basically, and we'll go through those steps. And then from then on, you can just multiply it by RC, say for a 65 nanometer process, and multiply it by the RC for a 90 nanometer process, and then 130 nanometer process. And you know, if the 90 nanometer process is fast enough, you wouldn't want to pay that premium to be in a 65 nanometer process. So for example, the cost of a 90 nanometer process, I'm going to have to go kind of a little bit from memory here. I think the mask set for a 90 nanometer process is around $350,000. And this just for the mask set. I mean, then you have to design the chips and so on. And then the 65 nanometer process is more like maybe $600,000-$700,000. So you want to save that $300,000 and use the coarser process if you can. And you don't want to do that if you figure that out after you've designed everything. It's too late because you got to make a choice between designing for the 90 nanometer or the 65 nanometer process. And so this is why you do this kind of hand calculation early on in the process. Okay, so let's do a simple, like an example here, okay, which is, you know, down here, of course, but you want to do, so we want to do a 3-input NAND. Okay, when we all try this. So 3-input NAND with transistors with chosen to achieve effective rise fall times resistance equal to a unit inverter. Okay, so once you guys try it, and then, you know, the response is right there, okay? And then we'll try to solve it together. Why don't you guys take about 5 minutes to try, take a shot at that. Okay, let's try to give it a shot. How about curling? Can I get your help? Curling? Might probably mispronouncing your name.
Sorry, I was away for a second.
No worries. Did I get your name right?
Yeah, my name is Curlin. Yeah.
Great. So do you want to take a shot at helping me solve this thing?
Uh, I'll try. I'm
Okay,
still a little confused myself, but
that's why we do examples. Perfect.
okay.
Okay, so first, do you want to talk me through what a 3-input NAND gate might look like?
Um,
Now, remember, so for a NAND gate, let me just, so for a NAND gate, let's go back a couple of steps, okay? Remember for a NAND gate, or the way for any gate, for any CMOS gate, we had the pull-up network and the pull-down network. And the pull-up network went to the supply, and the pull-down network went to ground. They had the same inputs, and that's the output. Do you remember all this stuff?
yeah.
Okay, great. And then, so the first step was when you want to do when you want any kind of gate, any kind of functionality, is you want to first figure out the pull down network, and we make the pull up network sort of the inverse of it. So if we have a 3-input NAND gate, so if we have A and B and C, okay, we would end up having 3 transistors in an AND configuration. Why is this in an AND configuration? Because for this to turn on, this whole path, this and this and this would all have to be on. Okay? And the reason it becomes a NAND is because then we connected the source to the ground. So basically, if this and this and this are all on, you get a 0 on the output. So that makes it a NAND.
Okay.
Okay, so let's just call the input something, I don't know, A, B, C. Okay, and then the what? Sorry, something is beeping on that. So just give me 1 second. Close the door. These days I'm going to do a face plant, you know. Still. Okay, so and then the pull-up network is going to be the complement of the pull-down network. Okay, so and so if the complements were, if this is the pull-down network, the pull-up, so if it was in series, the pull-up network would be in parallel. It would be the complement of it. Or vice versa, if the pull-down network was in parallel, which it would be in the case of a NOR gate, the pull-up network would be the complement of it, and that would be in series. Okay, so in this case, the pull-down network is in series. So the pull-up network is a complement of that, and it's in parallel. So you basically have our 3 CMOS pull-ups in parallel. So this guy is the pull-up network. And so it goes to VDD on one side. The other side goes to the output. And then the inputs go to both. So doesn't matter which is which here in this case. So we get this. So that ends up being our 3-input NAND gate. That was a very long-winded thing. So that's how you would get to a 3-input NAND or anything else.
Okay, that
Yeah.
makes sense.
Okay. So now, so we got that. Okay, so let's copy it over. Well, actually, let me leave that there. So it's asking, the problem's asking us is so now we got the NAND gate schematic. Now we got to pick the sizes of these transistors so that transistor width chosen so that the effective rise and fall is equal to a unit inverter. Okay, so the unit inverter is just looks like that, right? Just an inverter. So that's an inverter. You with me, Carl? So this is the in and this is out. Okay. Come on, stay with me, Carlin.
Yeah, I'm still here. I'm still here.
Okay. We'll do a call and response or whatever it is. In a unit, so that's an inverter. Okay, so you're good with that.
Yes.
So then a unit inverter is, now this is now you got to remember some of the stuff we did before the break, which is difficult. A unit inverter is when the NMOS is the smallest device you can get in a process, or we call this a 1X. That's code name for smallest device in a process. So for example, in our, sorry for the handwriting, guys, it's getting worse and worse. So for example, in our 180 nanometer process, the smallest device had a length of 180 nanometers and a width of 300 nanometers. I think that's what the layout rules dictated to us. Okay, so this is the 1X device, minimum device or unit device, has a length of 180 nanometer and a width of 300 nanometer. If you were in a different process, like a 65 nanometer processor or something else, then your unit device would be different, okay? And then the PMOS device is gonna be 2X the size of this. Why do we make it 2X? Is because the resistance of the PMOS, or you could think of it as the current through the current drive of a PMOS, is, so the resistance is 2 or 3 times higher than the resistance of an NMOS, or the other way to look at it is the current drive of a PMOS is 2 to 2 times less than an NMOS. So you would, to make the rise and fall time symmetric, okay, you would make this twice as wide as this. You would never mess with the length. The length you always want it to be the minimum, because anything else in a digital circuit is a waste. So we'll just make that. So L would stay at 180 nanometers, and the width would be 600 nanometers. Sorry. Okay. So, but well, it's just really saying this is to make, this stuff is not part of the problem. I'm just using a pretty specific process to give you guys as a, you know, to visualize or whatever. But basically, a unit size inverter is one where the N MOSFET is the minimum size and the P MOSFET is twice the minimum. Okay.
Okay.
Okay. Okay. So let me go to another victim. Anthony. Wanna hop on?
Hello, can you hear me?
Yep, can hear you, Anthony.
Yeah, no, I had to connect my mic. I had you to a speaker and then I had to connect you to a headset. But what's up, Professor?
Okay. So okay, so we want to size this guy. So that's we want
All right.
to have the same rise and fall resistances. So let's look at the pull downs. Okay, so we just look at the pull down. We have 3 guys in series. Okay. And we want to make the resistance of this the same as one guy. Right. So we want to make it the same as that guy. And we have 3 guys. So how would I size these guys? These 3.
You're asking like length and width wise?
Yeah. Now the length, don't mess with the length because we always want to make the length minimum length in visual design. But never, like almost never, you almost never want to make that non. Okay. So really we're asking about a width.
So it'd be like 900 nanometer.
But I'm for sure gonna focus on what's also the lessons.
Yeah, so what, like if I call this width of I don't know, if I call this 1x width, how much bigger would these guys be in width? Like what ratio? You're right on there. So it'd be a 3 width, right? 3x device.
Right, okay, yeah.
So in general, like you were right for a 180 nanometer process, it'd be 900. So when you add them in series, it'd be the same as that one. Okay, so how about the P MOSFETs?
And if it was 1 again?
So it'd be 1 here. Now remember, this guy is 2.
Right.
That's so, and you're trying to make these guys be similar to that.
So would they be all 2?
They'd be all 2, exactly.
Okay.
So because we're looking at the worst case pull-up case. Thanks, Anthony. That was thanks. So we're looking at, so there's only one case of a pull down, which is all these 3 devices being on. Okay. So in that case, you know they have to be 3x, 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 so that when they're all on, this equivalent resistance is going to be so 1 over R equivalent is going to be this is going to be 1 over 1/3 plus 1 over 1/3 plus, am I doing this right? Am I screwing this up? So if this equivalent, so so each one of these, whoops, I'm gonna make sure I'm doing this right. So this R equivalent is 1/3 R sub n. This is 1/3 R sub n, and this is 1/3 R sub n. So in total, when this device is on, I got all these guys adding up to each other. So is equal to R sub n. And so there's only one way to do it. Now, when we have the pull up in parallel, notice that you can have a whole bunch of different resistances. You could have only one of these guys on to pull up. You could have two of them on, or you could have all three of them on. But when you're looking at delays, we're looking at the prop delay. So for a propagation delay, it's worst case. And the worst case pull up is only when one device is on. Okay, when one device is on, the equivalent resistance is, or equivalent is 2 times, or sorry, 1/2 2 times R sub n. Okay, so the resistance of a PMOS that's 1x size is 2R sub n, because it has twice the resistance of a equivalent NMOS. But because we're having a 2x size, it ends up having the resistance. So in aggregate, it also ends up being R sub n. Okay, so pull up and pull down ends up being the same. Okay, guys, does that make sense?
Yeah.
Honestly,
Professor, could you explain again why NMOS is 3x? Or 3 times? Sorry.
In terms of why we make it 3 times wider?
Yeah.
Yeah, okay. So basically what we want to do is, the problem is asking for something that has the same resistance, like a 3-input NAND gate that has the same pull down and pull up resistance as an inverter, as a unit inverter. Okay, so the unit inverters pull down is just a unit with n MOSFET. Okay, but
Okay.
the problem with a NAND gate is that on the pull down, to get the logical functionality of a NAND, we have to have 3 n MOSFETs in series. Okay, so that's in our model of rise fall times. That's like having 3 resistors in series. Okay, when they're all on. So this looks like, this will have, so it's to get 3 resistors in series to have the same resistance as 1 resistor, you have to make each of them 3 times higher resistance, 3 times lower resistance. When they all turn on, they all add together, and then they end up having the same resistance as just a one resistor.
Okay. Yeah, I see now. I understand. Thank you.
So the wider you make a device, the resistance goes down by that same amount. So if you make something 10 times wider, the resistance goes down by a factor of 10.
Right. Okay, makes sense. Thank you.
Okay, so that gave us this guy. Okay, so that was the answer. So now the next one is, it wants us to come up with all the values for the capacitance and all this kind of stuff. So let's do that. Okay, let's annotate this guy. This gets really, so you guys gotta focus, because this doesn't require that much focus, but just keep going back to this model. Where's our model? just keep going back to this model, okay? So when you're trying to figure out capacitances and resistances. So I'll just overlay it on this one. So this, let's start with this input. This input is connected, so I'm gonna put a dot here, connected to that guy. So when I look at the gates, this guy here is 3 times wider than a minimum device. So its gate capacitance is going to be 3 times larger than a minimum device. Okay, so that guy. And this PMOS is twice as wide as a minimum device. And so it's going to have gate capacitance is going to be 2C. Okay, so every one of these inputs, so this guy connects to this. So this is going to have a 3C and 2C. Okay, and then this guy is also going to have a 3C and a 2C. Okay, so those are the capacitance on the input. Now let's look at the capacitance on the output side. So here, this source is going to have this lowest N MOSFET is 3 times the capacitance of a minimum device, the source is. Now, if we could get 2 different possible capacitances here in this node. Okay, if we did a bad job on the layout, if we had drawn that as 2 separate transistors, and then connected them up with metal, in that case, we would have 3 times the capacitance of this guy plus 3 times the capacitance of this guy, because the 3 times the capacitance, because these are 3 times wider than the minimum size. But if we do a better job, remember, because these are series devices, we can merge their source drain. So we could have just drawn it as a merged device. Meaning that this capacitance is kind of the capacitance of just one of these 2, because we merged them. So let's just assume we did it in that way, so that we did a better job of designing this thing than 2 separate guys. So this just ends up being 3C. And let's say we did a similarly good job on the layout here. We get 3C here. Now, on this output node, there's no way to merge the diffusion capacitance of an NMOS with PMOS. So here for the NMOS, I get 3C. Okay, and unfortunately for the PMOSFETs, we can't really merge those really either, because they are in parallel. So I end up getting, for the PMOSFETs, let me put those in a different color, orange. So I end up getting 2C for each. And I get similar capacitances here, but since it's going to VDD, it doesn't really matter what this capacitance here is, because this node is hooked up to VDD. Both sides of this capacitor are hooked up to VDD. Okay. So these guys don't matter. And also this guy, it's both sizes is capacitor hooked up to ground, so this guy also doesn't matter. Okay, so did I get this? So it's 5. So this the inputs all sum up to 5C. Okay, that's this 5C. And then the output is 6C here plus 3C, and that's 9C on the output. And I guess these guys also assumed that we did a good job on these intermediate nodes to get 3C here only. Okay. So everybody see how those capacitances kind of summed up in a model of the transistor? Any questions?
None so far.
Okay. All right, guys. Okay, so next comes, okay, so what do we do here? So now if you want to figure out this delay, what we would do is we would start plugging in the resistors here, right? So this would be R sub n over 3. Because these are 3 times the minimum width, right? So I'm just going to look at a pull down here. And then I got these capacitances, 3C, 3C, 9C. So let's just say I'm looking at the RC, so the fall time of, assuming that we can just use these equivalent resistors here, right? So now it's kind of like complicated to analyze because we have these intermediate nodes. So it's not so straightforward to do the RC calculation. Now there's this thing called Elmore delay, and I looked this up. I guess it's like sort of a mathematical thing. And basically the idea is that if you have this type of RC ladder, look at this ladder, looks a lot like our ladder here. Okay, so assuming this is sort of think of this as this being the input, and it's propagating this ground needs to propagate all the way to the output, and I have these resistive capacitive nodes. Okay, the Elmore delay model says that I can approximate that delay as the RC, so this RC, and then I sum the R2, R1 and R2 times C2. Okay, and then I sum the rest times C sub n. So here, if I wanted to get the fall time delay of this, it would be this guy times this. So the Rn over 3 times 3C plus Rn over 3 plus Rn over 3. Times 3C plus all these guys added together. So I'm just going to write it longhand so you guys can follow what I'm doing. Times 9C. Okay, so it would look like, I guess we could do this, it'd be RC plus, this is 2RC plus This is 9 RC. So it would look like 12 RC. Okay, so this is this Elmore delay algorithm. I don't know, is this an algorithm or I don't know, whatever, approximation, whatever you want to call it. So whenever you have this type of ladder network, this is what the Elmore delay says. You have these sort of this RC, 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 you can approximate the equivalent delay as, you know, this approach that we just took. So this guy times that, this guy times that, this guy times that, all of them sum together as you go through the network. Okay. So you can see when you're looking at the delay, sort of I forget something. Oh, sorry. Okay. Yep. So now it's the example is, now this is looking at the prop delay fall. So look at, this is kind of what I drew there, right? So the addition, this is what I panicked there for a second. It's also saying what happens if you drive H copies of yourself. So that the input capacitance of this guy, remember the total input capacitance was 5C. So if you're driving another gate like yourself, that's, you got to drive 5C of extra capacitance. And then if you're driving H of those, you're driving 5HC of extra capacitance. Okay. And so they go through and do the same thing like we did. So on the pull, this is on the pull down side. They divide, you know, got the resistance of each of these guys in the caps, right? And then they summed it up in the Elmore model, okay? Except that in this last capacitance, they added this 5HC to our 9C. So they added this 5HC to the 9C that we did. And you end up basically with this fall delay for a 3-input NAND gate. Okay. And this is, you can do the same thing with the PMOS FETs, and you get the prop delay rising. Okay. So the nice thing here is that, okay, so this, if you had a, this is like if you made a NAND gate that had the equivalent rise fall times of a minimum size inverter, okay, a unit size inverter, you would always get this delay, okay, get 12 plus 5H RC, okay. So let's say for the sake of discussion, let's say that I'm only driving one other device like myself. So H is equal to 1. So I ended up having 18 RC, okay. Now, if I'm in a 65 nanometer process, the delay here is going to be 18 times whatever RC I figured out, calculated here. What was it? 1.25 picoseconds. And if I was in a 180 nanometer process, it would be 18 times 5.5 picoseconds. So that's kind of the nice thing about this approach is it's, you know, you can use this as, you know, a generic calculation of a gate, in this case, 3-input NAND gate of a certain size. And then you can plug in these RC values for different processes to figure out what the delay would actually be, okay? So, Now, we talked about the fall time delay always has to be the same because there's only one way to get a falling output, right? You go from, because all of these have to be on before this output goes from high to low. But there is a bunch of different ways to get a rising gate in an AND gate. Specifically, there's like, assuming there's no layout differences between these guys, there is, either having this guy and, well, it could get kind of more complicated, but if you have one of these guys on, two of these guys on, or three of these guys on, or those are the possibilities. So the prop delay, if you guys remember, the definition of prop delay was the longest delay from input to output. And the definition of the contamination delay was the shortest delay from input to output. So for the N MOSFETs, when you're falling, the contamination delay and the prop delay are the same thing. There's only one way to do that. But when you're talking about the PMOS rising outputs, the propagation delay is the worst case delay, meaning that only one device is on. And the contamination delay being the fastest delay means all three are on. Okay, so each one of them would have a different delay. And that's what these different sort of, when you're talking about contamination delay versus propagation delay on the PMOS FETs, you basically assume that you have all three PMOS FETs on, and it reduces the delay for the rising. Okay, so that's the contamination delay. Okay, versus these are like this for the same thing. This would be the propagation delay. So this is 9 plus 5H, and this is 3 plus 5/3 H. So significantly lower resistance or lower delay when all three devices are on. Okay. Now the delay also, you can divide this into two components. There is what's so-called the parasitic delay. That means if I had a 3-input NAND gate not driving anything, it would have a delay through it, okay, with no load. And that's called the parasitic delay. It's the delay of the device itself. And then the effort delay is if I was driving a load. Okay, the delay of that extra delay for driving that load. And typically that load is capacitive, but it's typically what it is a bunch of other devices. Now, it could be devices like yourself, or which is the easiest one to define, or it could be a bunch of other devices. Could be, God knows what. Bunch of NOR gates, whatever it is that this logic functionality is doing. And that's called the effort delay. And you'll see you can sort of treat them differently. Okay, this just talks a little bit about, laying these things out. And, we talked about sharing. So you can see this is the 3-input NAND gate. And these are the 3 N MOSFETs. And because they're in series, we've shared these nodes. So the capacitance has gone down significantly. There's not a lot you can do with sharing of the PMOSFET gates, so that didn't really change. Okay, and that brings us to the end of this delay lecture. Okay, any questions, guys?
Pretty cleared up.
Okay, all right. So now we go to, let's go Okay. So now we move on to the topic. So we talked about, lecture 7 talked about noise margin. That was the first thing when we looked at the transfer curves of devices. And we just talked about delay. Now we're going to talk about the other figure of merit for a design, which is power consumption. Okay, if you guys remember, the figures of merit for a design were how robust the design was. That's kind of from a noise margin standpoint. How fast your circuit ran, that was in performance. Cost of the design, it kind of comes down to mostly layout, how big your circuit is. And then lastly, the power consumption that you pick. And now we're talking about power consumption. Okay, so before we talk about that, before we talk about power consumption, we want to, come up with like a few, it's not really definitions, but we have to do some things to make the calculations a little bit easier, as you guys will see. Okay, so let's see. So we want to talk about instantaneous power, energy, and average power. Okay, so let's say in a typical situation, if I was going to put a scope probe on a power supply in your chip or FPGA or whatever. So this is the power supply. The power supply would be at, let's say for the sake of discussion, it's a pretty good power supply. So it would be at 1.8 volts. And then if I put in another axis here, and this would be the current to the power supply, you would see you'd see the current fluctuate going through the power supply, okay? If you remember circuits that are on or turning on, they pull current. The ones that are off, the circuits that are off, aren't pulling current. So at any point along here, at any one point, there's a different set of circuits that are on, different set of circuits that are turning on, turning off, etc. So the current going through the supply is constantly fluctuating. Okay, so if I look at this instantaneous power, I can define an instantaneous power at any point here, and it'll be slightly different. So, for example, if I'm here, and this, by the way, this power definition is current times voltage, right? So the voltage, for the sake of discussion, we're saying the voltage stays the same, VDD. But at any one point, the current's changing. So for example, here the current's fairly low, and here the current's fairly high. So the instantaneous power here is going to be lower than the instantaneous power there. And so that's basically VDD times I as a function, IDD, let's say, as a function of time. Okay, so that's instantaneous power at any particular point in time. Okay, now energy is defined as the average I think it's just not really the average, it's the total power. It'll be, you can define energy as being over a particular length of time. So if I look at this length of time, my energy would be, so let's call this time t. My energy would be the instantaneous power integrated over that time. Okay. And the reason I went through that is because the average power, to get the average power, I would first have to calculate the energy and divide it by that same period. Okay, so it would be 1 over T times 0 to T. Okay, so I'm calculating the average energy over this period and then dividing it by the total time during that period to get the average power. So this is what you would do, for example, if you wanted to figure out how long it would take for your battery to discharge on your iPhone or whatever. You couldn't take the instantaneous power just by itself, because the iPhone, when it's running in different modes, when you're in a dark room, the display might be brighter. When you're in a bright room, it might be lower, so on and so forth. Your camera may be on, maybe it's not on. So the instantaneous power goes up and down significantly. So if you can't use the instantaneous power of your worst case scenario to figure out how long your battery is going to go off. You have to come up with an average power to figure that out. And that's what you do. And that's why you end up with like an average power type of calculation. Okay, so now let's look at how are we doing on time? Let's look at the power in different sort of circuit elements. Okay, if you have a power supply, this is the instantaneous power, which is just as we talked about, would be the current in that supply times the voltage of the supply, assuming it's constant. Okay, and if you have a resistor power is always, so this is power. These are all sort of different definitions of power. I times V, or it could be V squared over R if you have a resistor. Okay, and then a capacitor, because there's no definition of power through a capacitor, you can figure out the energy to charge and discharge the capacitor. Okay, so you would end up looking at how much energy it would take. This goes from 0 to infinity in time, but really we're only interested in. So let's start with this. So you start looking at the total energy to charge this capacitor for the sake of discussion. Okay, and this IT, because Q is equal to CV and dQ dt is C dV dt. That's I. So you can replace I of t with C dV dt here. Okay, and integrate. And then if we wanted, we can also, this is in terms of time, but if we're saying how much energy does it take to charge this capacitor to a certain voltage, we can just integrate over the limits of the voltage in terms of instead of integrating in terms of time, because we're just charging up or charging down. So we can take the same integral, go from 0 to Vc, which is what we're charging it up to as a function of Vt, and we end up with this 1/2 CV squared as the energy to charge a capacitor of certain capacitance to a certain voltage V sub C. Okay, I'm just doing sort of simple math there. All right, so let's stop there, because I think the next thing is we're going to see how this applies to an inverter driving a capacitance, and we're going to get kind of deep into it. Okay, guys, any questions about the lecture today?
I'm good.
No? Okay, guys. All right. Well, have a good weekend.
Thank you, Professor.
Thanks. Bye.
Bye-bye.
Have a good one, Professor. Thank you.